Have you ever looked up at the night sky and wondered where it all stops? Beyond the stars, beyond the galaxies, beyond the edge of everything we can see. What lies there? Is there a wall, a boundary, a final frontier? Or does space simply go on forever, stretching into an infinity our minds can barely grasp? Tonight, we drift toward that question, toward the edge of comprehension itself, to ask not just where space ends, but whether end even has meaning in the cosmos. So close your eyes, let the vastness settle around you like a gentle blanket, and follow me to the furthest reaches of existence. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin with the first question. Part 1. How far can we actually see? When you gaze up at the stars tonight, you're looking back in time. The light from those distant suns has traveled for years, centuries, sometimes millions of years to reach your eyes. You're not seeing the stars as they are now, but as they were when that light began its journey. The universe, in this sense, is a time machine built from photons and distance. But there's a limit to how far we can see, not because our telescopes aren't powerful enough, but because the universe itself has an edge in time. According to NASA's Goddard Space Flight Center, the observable universe extends about 46.5 billion light-years in every direction from Earth. That might seem impossible at first. After all, the universe is only 13.8 billion years old. How can we see farther than light has had time to travel? The answer lies in expansion. While light has been traveling toward us, space itself has been stretching, carrying distant galaxies farther away. The light that left those galaxies 13.8 billion years ago has been racing through expanding space all that time, and the galaxies themselves are now much farther than where they were when the light departed. This boundary of visibility is called the cosmic horizon, or more precisely, the particle horizon. It's the sphere beyond which light hasn't had time to reach us since the Big Bang. ESA's Planck satellite has mapped this edge with exquisite precision, measuring the cosmic microwave background, the faint afterglow of the universe's birth. That ancient light has been traveling for nearly 13.8 billion years, stretched by expansion into microwave wavelengths. It's the oldest light we can ever see, the final echo of creation. But here's the profound truth. The cosmic horizon is different for every observer. An alien civilization in a galaxy 10 billion light-years away would see a different sphere of visibility centered on them. There's no universal edge, no single boundary that all observers share. The edge of the observable universe is personal, defined by where you stand and how long light has had to reach you. The James Webb Space Telescope, JWST, now peers deeper into this cosmic ocean than ever before. It has captured galaxies that formed just 300 million years after the Big Bang. They're light redshifted and ancient. These galaxies are among the most distant objects we've ever observed, yet they're still within our cosmic horizon. Beyond them lies a realm we cannot see, not because it's empty, but because its light hasn't arrived yet. What lies beyond our horizon? More galaxies, more stars, more worlds. The universe doesn't end at the edge of our vision. It continues, as vast and full of structure as the part we can see. But we'll never know what's there directly. Those regions are forever beyond our reach, separated not by space alone, but by the expansion of space-time itself. As cosmologist Brian Greene once said, "The universe is under no obligation to make sense to you." Our cosmic horizon is a reminder of that truth. We live inside a sphere of visibility, bounded by time and expansion, looking outward into a darkness that holds secrets we can never unveil. Take a slow breath. Right now, the most distant light we can see is still traveling toward us, carrying images of galaxies long transformed or destroyed. And beyond that light, in regions we cannot observe, the universe continues its silent expansion, creating space we will never explore. And as we consider the limits of what we can see, a deeper question emerges. If we can't see beyond our cosmic horizon, does that mean space ends there? Or is there something more, something infinite? That's where our next chapter begins. Part 2. Is the universe finite or infinite? The question sounds simple, but it touches the very foundation of reality. Does space have an edge, a final boundary beyond which there is nothing? Or does it stretch on forever, an endless expanse without beginning or end? For centuries, philosophers and scientists have wrestled with this mystery, and even today, the answer remains uncertain. According to Einstein's general theory of relativity, the shape and size of the universe depend on its total energy and matter content. If the universe contains enough mass and energy, gravity will curve space into a closed shape, like the surface of a sphere. In such a universe, you could travel in one direction and eventually return to your starting point, much like circumnavigating the Earth. This universe would be finite in size, but without edges. There's no boundary to cross, just as there's no edge to the surface of a balloon. But if the universe contains too little mass, space curves in the opposite way, creating an open saddle-shaped geometry. In this scenario, the universe would be infinite, stretching forever in all directions. Between these extremes lies a flat universe, where space follows the familiar Euclidean geometry we learn in school. A flat universe could be infinite or finite, depending on its topology, whether space loops back on itself in some strange way, or simply goes on without end. So which is it? Observations from ESA's Planck satellite and NASA's WMAP mission have measured the universe's curvature with extraordinary precision. The data shows that, as far as we can tell, the universe is remarkably flat. The curvature, if it exists, is so slight that it lies beyond our ability to detect. This suggests that space might be infinite, extending forever beyond our cosmic horizon. But flat doesn't necessarily mean infinite. Mathematicians have shown that space could be flat yet finite, wrapped into complex shapes called topologies. Imagine living on the surface of a torus, a donut shape. An ant crawling along that surface would experience flat geometry locally, yet the surface itself would be finite. The universe could be similarly shaped, looping back on itself in ways we can't perceive from our limited vantage point. In 2003, astrophysicist Jean-Pierre Luminet and his colleagues proposed that the universe might have the topology of a dodecahedron, a 12-sided shape where opposite faces connect. If true, light traveling in a straight line would eventually return from the opposite direction, and we might see multiple images of the same distant galaxies. Searches for such repeating patterns have found no conclusive evidence, but the possibility remains. NASA's Nancy Grace Roman Space Telescope, set to launch in the coming years, will survey the universe with unprecedented precision, searching for subtle hints of finite topology. If space loops back on itself, the distribution of galaxies might reveal faint patterns, echoes of structure repeating across the cosmos. Yet, if the universe is truly infinite, the implications are staggering. An infinite universe means infinite matter, infinite galaxies, infinite stars. It means that somewhere, impossibly far away, there could be another Earth, another you, living a life identical or subtly different from your own. This isn't science fiction. It's a consequence of infinity. In an infinite space with random variations, every possible arrangement of matter must occur, not just once, but infinitely many times. Cosmologist Max Tegmark has calculated that in an infinite universe, There could be an identical copy of you about 10 to the power of 1029 meters away. Of course, such distances are so vast, they make the observable universe seem like a grain of sand. These copies exist in principle, but we can never interact with them, never know they're there. The idea is both humbling and unsettling. If space is infinite, then the universe doesn't just contain everything we see. It contains everything that could possibly exist. Every variation, every possibility, every choice plays out somewhere in the endless expanse. But there's another twist. Even if the universe is infinite now, it might not always have been. During the Big Bang, space itself was created and has been expanding ever since. If space is infinite today, it was also infinite at the moment of creation, just more densely packed. Infinity doesn't grow. It's already limitless. The Big Bang didn't happen at a point. It happened everywhere, filling all of infinite space with energy and matter. As physicist Sean Carroll explains, the Big Bang is not an explosion in space, but an explosion of space. Understanding this distinction is key to grasping how an infinite universe could have a beginning in time, but not in space. Take a quiet breath. The universe might stretch forever, or it might loop back on itself in ways we can't yet detect. Either way, what lies beyond our vision is far stranger and more vast than we can easily comprehend. And as we ponder infinity, another question arises. If space is expanding, what is it expanding into? That's the mystery waiting in our next chapter. Part 3. What is space expanding into? One of the most common questions about the universe is also one of the most misunderstood. If space is expanding, what is it expanding into? The question feels natural. After all, when a balloon inflates, it grows into the surrounding air. But the universe isn't a balloon floating in some larger space. It's space itself that's expanding, and there's no outside for it to grow into. This is one of the profound insights of Einstein's general relativity. Space isn't a container that holds things. It's part of the fabric of reality, woven together with time into what physicists call space-time. When we say the universe is expanding, we mean that the distances between galaxies are increasing, that the fabric of space itself is stretching. There's no edge to cross, no exterior to expand into, because there is nothing outside. Imagine you're an ant living on the surface of a balloon. As the balloon inflates, the surface stretches, and the distance between any two ants increases. But the ants don't move through the surface. They stay in place while the surface itself expands. From their two-dimensional perspective, there's no inside or outside of the balloon, just the surface. The universe is similar, but in 3 dimensions. We live within space, and as space expands, galaxies drift apart, carried by the stretching fabric. This expansion was first discovered by Edwin Hubble in 1929. By observing distant galaxies, Hubble noticed that nearly all of them were moving away from us, and the farther they were, the faster they receded. This relationship, now called Hubble's law, revealed that the universe isn't static. It's growing, and has been since the Big Bang. NASA's Hubble Space Telescope and ESA's Gaia mission have refined these measurements, showing that the universe is expanding at about 70 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space is stretching at 70 kilometers per second. Galaxies billions of light-years away are receding faster than the speed of light, not because they're moving through space that fast, but because the space between us is expanding. This leads to a strange consequence. There are galaxies we can see today whose light will never reach us again. As space expands, some regions move away faster than light can travel. The cosmic horizon is not just a boundary of visibility, it's also a horizon of causality. Events beyond it can never affect us, and we can never affect them. But if space isn't expanding into anything, does that mean the universe is all there is? Not necessarily. Some cosmologists propose that our universe is just one among many, each existing in its own separate space. These parallel universes, if they exist, wouldn't be outside our space in any meaningful sense. They'd be disconnected regions, perhaps with different physical laws, different constants of nature. This idea, called the multiverse, remains speculative, but it's a natural consequence of some theories, particularly eternal inflation. According to inflationary cosmology, the Big Bang was preceded by a brief but intense period of exponential expansion called inflation. During this phase, quantum fluctuations in space caused some regions to stop inflating and form universes like ours, while others continued expanding forever. Each bubble that stops inflating becomes a separate universe, disconnected from the others. From inside our bubble, we can never see or reach the others. They're not beyond our cosmic horizon. They're beyond the structure of space-time itself. As physicist Alan Guth, who proposed inflation theory, once said, "Inflation makes the universe infinite, or at least very, very large." If inflation is correct, our observable universe is just a tiny patch within a vastly larger structure, possibly one of countless patches in an endless multiverse. Yet, even if the multiverse exists, each individual universe still doesn't expand into anything. Each bubble of space is its own self-contained reality. The question, what is space expanding into, turns out to be based on a misunderstanding. Space isn't expanding into a pre-existing void. Expansion is an intrinsic property of space-time, a stretching of distances, not a motion through some external medium. This is hard to visualize because our brains evolved to understand motion through space, not the expansion of space itself. We think in terms of objects moving from one place to another. But space-time expansion is different. It's the stage itself changing size, not the actors moving across it. Take a slow breath. Right now, as you sit here, space is expanding around you. On cosmic scales, galaxies drift apart, carried by the stretching of the universe. But locally, within our galaxy, gravity holds everything together. The expansion is gentle, patient, inevitable. And as we consider this expansion, another question emerges. If space has been expanding since the Big Bang, will it ever stop? Will the universe reach an edge, or will it expand forever? That's the question waiting in our next chapter, Part 4. Will the universe expand forever? The universe has been growing for 13.8 billion years, and it shows no sign of slowing down. In fact, recent observations suggest the opposite. The expansion is accelerating. This discovery, made in 1998 by two independent teams studying distant supernova, shocked the scientific community and earned the researchers the Nobel Prize in Physics. Something is pushing space apart faster and faster, and we call that something dark energy. Dark energy is one of the deepest mysteries in cosmology. It's not a substance or a force in the usual sense. It's a property of space itself. As space expands, more dark energy appears, filling the new volume and driving even faster expansion. According to ESA's Planck satellite, dark energy makes up about 68% of the universe's total energy. Dark matter, the invisible substance that holds galaxies together, accounts for 27%. Ordinary matter, stars, planets, gas, dust, everything we can see, makes up just 5%. What is dark energy? The simplest explanation, proposed by Einstein himself a century ago, is the cosmological constant. In his equations, Einstein included a term representing a constant energy density filling empty space. At first, he thought this was a mistake, calling it his greatest blunder. But modern observations suggest he was right. Space has an inherent energy, a vacuum energy that pushes outward, counteracting gravity's inward pull. If dark energy remains constant, the universe will expand forever, faster and faster. Galaxies beyond our local group will accelerate away until they vanish beyond our cosmic horizon, their light stretched to infinite wavelengths. In trillions of years, the night sky will darken, distant galaxies will disappear, and future civilizations might look up and see only the stars of their own galaxy, unaware that a vast universe once surrounded them. NASA's Dark Energy Survey and ESA's Euclid mission are mapping the universe's expansion history, measuring how fast space grew at different times. If dark energy's strength has changed over cosmic history, it would reveal something profound about its nature. So far, the data shows that dark energy behaves like a cosmological constant, unchanging and relentless. But there are other possibilities. Some physicists propose that dark energy might decay over time, weakening until gravity eventually halts the expansion. In this scenario, the universe might reach a maximum size and stabilize, neither expanding nor contracting. A static cosmos, balanced perfectly between growth and collapse. Another idea, more dramatic, is the Big Rip. If dark energy strengthens over time, the expansion could become so violent that it tears apart galaxies, stars, planets, even atoms. In this scenario, the universe ends not with a whimper, but with a ripping of space-time itself, shredding reality into quantum fragments. Or the universe might collapse. If dark energy is temporary, gravity could eventually win, pulling galaxies back together in a big crunch. Space would shrink, temperatures would rise, and eventually, the universe would return to the dense, hot state from which it began. Some cosmologists, like Roger Penrose, have proposed that the Big Crunch could transition smoothly into a new Big Bang, creating a cyclic universe that expands and contracts eternally. Each of these scenarios depends on the nature of dark energy, which remains unknown. The James Webb Space Telescope is now observing the most distant supernova and galaxies, tracing the universe's expansion back to its earliest days. By comparing expansion rates at different cosmic times, scientists hope to determine whether dark energy is constant or evolving. For now, the most likely fate is eternal expansion. The universe will grow colder, darker, emptier. Stars will burn out. Galaxies will drift apart. In the unimaginable future, only black holes will remain, slowly evaporating through Hawking radiation. And when the last black hole disappears, the universe will enter a state of maximum entropy, a featureless expanse of nearly uniform radiation, devoid of structure, energy gradients, or change. Physicists call this the heat death of the universe, the final equilibrium. It's not an end in the sense of destruction, but an end to complexity, to life, to anything happening at all. Time would still pass, but nothing would change. The universe would exist in eternal stillness. Yet even in heat death, quantum mechanics suggests something strange. Virtual particles would still fluctuate in and out of existence. And over timescales so vast, they dwarf the current age of the universe. Random fluctuations might spontaneously create new structures, even new universes. As cosmologist Lawrence Krauss once said, "The universe came from nothing, and it will return to nothing, but even nothing is something." The boundary between existence and non-existence is blurrier than we think. Take a quiet breath. The universe's end, if it has one, lies trillions of years in the future. For now, stars still shine, galaxies still turn, and life still finds its way. The end, if it comes, will be gradual, patient, and silent. And as we consider these distant futures, a final question emerges. If space might expand forever, might there also be other spaces, other universes, beyond our own? That's the mystery waiting in our last chapter. Part 5. Could there be something beyond our universe? The idea of multiple universes, once confined to science fiction, has become a serious topic in cosmology. If our universe is not alone, if there are other realms of space and time beyond our cosmic horizon, then the question, where does space end, takes on new meaning. Perhaps space doesn't end. It merely branches, fragmenting into countless separate realities. The multiverse hypothesis arises from several lines of theoretical physics. The first is eternal inflation. If inflation, the rapid expansion that occurred moments after the Big Bang, is driven by a quantum field, then it might never stop everywhere at once. In most regions, inflation continues forever, but in some pockets it ends, and those pockets become universes like ours. Each universe is a bubble in an eternally inflating sea, forever separated from the others. According to physicist Andre Linde, one of the architects of inflation theory, the multiverse is not just possible, it's inevitable. Inflation is eternal into the future, he says. It produces an infinite number of universes. From inside one bubble, we can never see or reach the others. They're not beyond our horizon in space. They're beyond the structure of causality itself. Another source of multiverse ideas is string theory. In this framework, the fundamental building blocks of reality are not particles, but tiny vibrating strings of energy. String theory requires extra dimensions of space, up to 10 or 11 dimensions in total. The extra dimensions are hidden, curled up so small we can't detect them. But how they curl determines the physical laws and constants of our universe. Different configurations of these hidden dimensions might create different universes, each with its own physics. There's also the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. In this view, every time a quantum event occurs, every time a particle decays, a measurement is made, or a choice is observed, the universe splits into multiple branches. Each outcome happens, but in separate, non-interacting worlds. If true, reality is a vast, branching tree of universes, all equally real, all existing in parallel. These ideas are speculative, and many physicists remain skeptical. The multiverse is difficult to test because, by definition, we can't observe other universes. They're beyond our reach, shielded by the structure of space-time or the branching of quantum probabilities. Some critics argue that if a theory makes no testable predictions, it's not science, it's philosophy. Yet, there are subtle ways the multiverse might leave traces. If another universe collided with ours in the distant past, it could have left a mark on the cosmic microwave background, a circular pattern or anomaly that the Planck satellite might detect. So far, no such evidence has been found, but the search continues. Another possibility is that the constants of nature, the strength of gravity, the mass of the electron, the speed of light, are not fixed, but vary from universe to universe. If so, our universe might be just one in a vast landscape of possibilities, each with different laws. Some universes might have stars and galaxies, others might be empty or chaotic, unable to support complexity or life. This idea, called the anthropic principle, suggests that we live in a universe suited for life simply because we couldn't exist anywhere else. In a multiverse with countless variations, observers like us naturally find themselves in the rare universes where conditions allow life to emerge. It's not that our universe is special, it's that we're selecting for the conditions we need to exist. As physicist Steven Weinberg once said, "If there is a multiverse, then we should not be surprised to find ourselves in one of the rare universes that can support life." The multiverse doesn't answer why the universe is the way it is, but it shifts the question, making fine-tuning less mysterious. NASA's upcoming missions, including the James Webb Space Telescope's continued observations and future gravitational wave detectors, might provide indirect hints of the multiverse. If cosmic inflation left patterns in space-time, Those patterns could encode information about the larger structure beyond our bubble. But even if the multiverse exists, it doesn't mean space ends. It means space is far larger and stranger than we imagined, a patchwork of separate realities, each with its own beginning, its own laws, its own fate. The question, where does space end, might not have a single answer. Space might not end at all, but fracture into infinite variations, each as real and vast as our own. Take a slow breath. The universe you know, the stars above, the earth beneath, might be one patch in an endless quilt of worlds, forever separated, forever alone. Conclusion: the edge we cannot cross. So where does space end? The honest answer is, we don't know. The observable universe has a boundary, defined by the distance light has traveled since the Big Bang. Beyond that horizon lies more space, more galaxies, but we can never see them. If space is infinite, it has no edge. It simply goes on forever. If it's finite, it might loop back on itself, creating a cosmos without boundaries. Space might be expanding into nothing because there is no outside to expand into. The universe might be one of many, part of a multiverse we can never observe. And the ultimate fate of space, whether it expands forever, collapses, or tears itself apart, depends on dark energy, a force we don't yet understand. What we do know is this: the universe is far stranger, far larger, and far more wondrous than our ancestors ever imagined. We live in a time when we can ask these questions, probe these mysteries, and glimpse, however faintly, the structure of reality itself. The edge of space, if it exists, is not a wall or a boundary. It's a horizon of understanding, a limit to what we can know. And perhaps that's fitting. The universe has given us enough to explore for thousands of lifetimes, enough mystery to fuel wonder for generations to come. Take one last, slow breath. The universe surrounds you, vast and ancient, stretching beyond sight, beyond thought, beyond imagination. And somewhere, impossibly far away, space continues, whether it ends or goes on forever, carrying with it the silent echo of the Big Bang, the slow dance of galaxies, and the quiet persistence of existence itself. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours. And if you're kind enough, please tell me in the comments where you are tonight and what time it is where you're listening. I love seeing how far these quiet adventures drift across the world, from one sleepy corner of the planet to another. Your words, your presence, even your silence, they're like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe hold you gently, and may its vastness remind you that you are part of something infinite, eternal, and endlessly beautiful.